4.6 talks about limits at infinity. So this is talking about asymptotes. We have two types, vertical and horizontal. Now, vertical asymptote and horizontal asymptote were discussed in either pre-calculus or college algebra when we talked about rational functions. So it's the same idea, but now we're just going to make it official. Back then, you did look at the highest power of the denominator, highest power at the top, and looked at the ratio. But now let's make it really a set way of figuring this out. Now, vertical asymptotes. So here, for the following exercise, examine the graph. Identify where vertical and horizontal asymptotes are located. Well, if you recall, vertical asymptotes are lines that a graph gets very close to but never crosses. So it seems for this problem, we have vertical asymptotes and we denote them by VA. That is at x equal, it seems, -3 and 2. And we have horizontal asymptote at y equal, it seems, 0. So here they're just making sure that if you can refresh your memory back from the days and figure out how these work. Well, same deal here. If I wanted to look at the vertical asymptotes, well, it seems the graph is getting very close to x equals 0. That's 1 and 2. So we have vertical asymptote, it seems x equals 0, 1, and 2. And horizontal asymptotes, the graph, now you notice there's only one horizontal asymptote normally. The graph is reaching that. All right. Now, algebraically, this is more like it, not off a graph. For the following functions, determine whether there is an asymptote at x equal 8. Justify, well, we're not going to use a graphing calculator, but this is what we know. You get a vertical asymptote. That's where the denominator equals 0. Basically, to show a restriction on the domain on a graph, you draw a vertical asymptote saying that these are values you can't reach. Now, I notice that x plus 1 cancels out. So this is really f of x equal 1 over x plus 4. If I was to sketch a graph of this, and that's not a requirement, I'm just going to show you. This is back from college algebra again. If I was to graph this, I'll say there's a vertical asymptote at -4. Now, as x approaches infinity, this will shoot to 0. There's a horizontal asymptote at y equals 0. If I replace x by 0, I'll get 1/4. So the graph looks like this. Again, that's not part of the problem. But the fact that there was a -1 in the denominator and you canceled it out, whoever's looking at this would know that at x equal -4, that makes the denominator equal 0, and you can't have that. But also you want to tell them, if they look at this, they think there's only -4, or if they look at the graph, they think only x equal -4 you cannot have. You want to tell them -1 you can't have also. When you put -1 in there, what do you notice you get? You get 1 over 3. So the way it works, if you remember back from the days, you go to -1 1/3, and you make that a whole. So a equal -1 is a whole on the graph. So they're asking, for the following functions, determine whether there is an asymptote. In this case, no. X equal -1 is not an asymptote. It's a hole on the graph, but it's not an asymptote. How about here? Well, to have an asymptote, you must have a denominator. And this graph looks something like this. I believe it looks like that, like a cusp. Not really. That is the square root of x plus 2 cubed. So our graph looks something like that. Either like this or like this. Either way, there is no asymptote there, so no. It's just not defined to the left of that. When I look at this problem, I'm looking at f of x equal 1 plus 1 over square root of x to the fifth. Again, at a equal 1, no. This will have an asymptote at x equals 0, if any. All right, for the following exercises, evaluate the limit. Now, the horizontal asymptote takes a lot longer. That's when you take the limit as x approaches infinity. And let me see really quick. So, the limit as x approaches infinity, that would mean, keep in mind, let's go here and review a few things really quick and pretty much set how this is going to work. So let's make sure, back in the days, again, you talked about this, maybe not depending on who you had, but if we talk about 1 over x, as x approaches infinity, if I pick x equal 10, that's 1 over 10, which is 0.1. And you should say plus or minus, because if you put negative 10, that's also negative 0.1. If I pick x equal 100, 1 over 100 is 0.01. If I pick 1,000, 1 over 1,000 is 0.001. As x approaches infinity, as x gets larger and larger, this gets closer and closer to 0. Well, think of it this way. If the top of the fraction is fixed and the denominator is growing, the bigger the denominator is, the smaller the fraction is. Actually, if I take the limit as x approaches a of any number over x, that would be 0. What? You know what I mean. Infinity. I meant infinity. The limit as x approaches infinity of any number, positive or negative, doesn't matter. If the top is fixed, even if that's a billion, the denominator eventually is going to grow over a billion, and that number will start reducing, and that will become 0. So that's the goal. The goal is to get a number over 0 to decide. So when I look at something like this problem right here, I say, well, here it's simple because I could split that up. Algebraically, I could do that. I could say that's 2x over 4x minus 5 over 4x. That is the limit as x approaches infinity of 2 over 4 minus 5 over 4x. And based on what I showed you, any quantity over x approaches 0. So you're left with the limit as x approaches infinity of 1/2. And the limit of the constant is the constant. And that's normally how you find a horizontal asymptote. So horizontal asymptotes take a lot more than vertical. What's the vertical asymptote? That's easy. That's where the denominator equals 0. X equals 0 is a vertical asymptote. We all know that. Horizontal asymptote, you have to take the limit as x approaches infinity, and that's how you determine how that works. Remember, positive or negative infinity doesn't matter because plus or minus 0 is still 0. 0 is the only number. When you say plus or minus, you're saying the same thing. Now here, I don't have the luxury of dividing or splitting them up. So the way I play this, so that I will never have an ambiguous case, I would divide every time I see a rational function in which the denominator is more than one term, which means I can't separate them algebraically. I divide by the highest power term of the denominator. So I divide this by the highest power term of the denominator is x squared. And let me elaborate why the highest power term of the denominator. If I divide by the highest power term of the denominator, I'm guaranteed that I wouldn't get a 0 in the denominator as the limit x approaches infinity. If I divide by the highest power term of the denominator, I'm going to always get a constant. I could deal with the top easily, and that's what it would look like. And if I take the limit as x approaches negative infinity, any quantity over 0 will disappear. I'm left with simply 3x over 1. And as x grows to negative infinity, 3 times that would be negative infinity. Normally, this is when you say you have a horizontal asymptote. Instead of a horizontal asymptote, you say you had an oblique asymptote, if you remember back in the days. Now, we get to absolute value, and there's a small trick with absolute value. I want to take the limit as x approaches infinity. So here, I want to divide by the highest power term of the denominator. The highest power term of the denominator, obviously, I would like to divide this by x squared, this by x squared. The top is 3x. So I'm trying to divide by the square root of x squared. Right? That's what I did for the bottom. That's what I do for the top. And that would be the limit as x approaches infinity. And let's see how that works. This will be the square root of 1 plus 1 over x squared. The top, wouldn't that be 3x over x? That'll simply be 3. Now, if x is positive, there's no problem with what I just did. If x is negative, I'm going to elaborate on that with this example when I get to it. It seems all the problems in the book that are even, they take the limit as x approaches positive infinity of a radical. And the odds touch on this idea, so I want to make sure that we touch on it, not n. X. All right, so here again, this approaches 0, and you're left with 3 over radical 1, which is 3. The horizontal asymptote for this graph is 3. And why is that important? Because when we do graphing pretty soon, if you could figure out that there's an asymptote, you know the graph is going to level off next to that number. And that makes graphing very easy. So if I know that, for example, this right here, on the long run is going to level off next to 3. If it's coming from the bottom, I'll know it's going to look like this. And if it's coming from the top, I'll know it's going to look like that. That's really important for me to figure out. On the long run, what's the graph doing? The same deal here. I'll say this is the limit as x approaches infinity. I'm going to divide by the highest power term of the denominator. In this case, that would be x squared under the radical. Whatever you do to the top, you do to the bottom. The top, so this is just 1 minus 1 over x squared. And again, since x is positive, there's no problem with you writing that as x. And the x's cancel out, and that's a 4. And the limit as x approaches infinity, that will be 0. So you're left with 4 over 1, which is 4. Here, I'm going to take the limit as x approaches infinity. And I'm going to divide by the highest power term of the denominator, which is x. I'll get the limit as x approaches infinity. Again, that's a 1. Now, if you cancel those, this is 1, this is 1 half. You have a half left in the denominator, and you have a half left in the denominator. As x approaches infinity, that approaches 0, 0, and 0. You're left with 0 over 1 minus 0 plus 0. Basically, 0 over any non-zero number is 0. So this graph levels next to the x-axis. Now, we want to get to this problem. And again, here we have to get an idea clear out of the way. So, if I told you that if, this is a side note, if I told you that x is less than 0, x is always negative, if I told you that. If you decided to take this x and write it as a square root of x squared, and I'm telling you that x is always negative, so basically what you do, you square it and square root it. By squaring it, you made it positive. This right here, x is bigger than 0. For example, if I let x equal negative 3, if you take negative 3 squared square root, that's the square root of 9. That's 3. To ensure that x will always be negative, if you ever had to take an x and write it as a square root of x squared, you have to make sure that it's always negative by putting a minus in front of it. Now notice here, I'm taking the limit as x approaches negative infinity. So the top, no issue. When I get to the bottom, this is 9x squared plus 3x. This is 2x. So I want to divide this by x and this by x. I want to divide this by x, right? And remember, What's x? X is like, let's say, negative 1,000. Then this x is always minus, always negative. When I divide this by an x, well, I want to make sure that x is always negative. So whatever this number is, it's always negative. If I'm going to have to take 1 over x in there, the only way to get it under the radical is to write it as 1 over square root of x squared. And to do that, well, I want to make sure it's a minus, so I put a negative. So the only way I could do that when I combine the two radicals is to put a minus there and then divide by x squared. And now I would say, look, that's the limit as x approaches negative infinity. This is 2. This is 5 over x. This is negative the square root of 9 plus 3 over x. This will approach 0. This will approach 0. And I'm left with negative square root of 9 over 2, or simply negative 3/2. So the horizontal asymptote for this problem will be negative 3/2 if you're approaching negative infinity. Here they say for the following exercises, find the horizontal and the vertical asymptote. The vertical asymptote, I think it's straightforward. Vertical asymptote, basically, where does the denominator equal 0? The denominator equals 0 at x equal plus or minus 1. We have 2 of those. Horizontal asymptote, if you remember back in the days, you had to do more work. And here you would divide by the highest power term of the denominator. Any quantity over x will approach 0. And you get 0, and that would be my horizontal asymptote. Whatever that limit is, let me do that again to this problem. Here, if I take vertical asymptote, none. The reason for that, the denominator can never be 0. Horizontal asymptote, y equal, I'll take the limit as x approaches infinity of x squared plus 3 divided by x squared plus 1. Divide by the highest power term of the denominator, which is x squared. So I'm looking at 1 plus 1 over x squared, 1 plus 3 over x squared. That's a 0, that's a 0. And I'll get 1 over 1. So I'll say y equal 1 is a horizontal asymptote. That's simple. And if I look at this problem, what is the vertical asymptote? Basically the domain, again, that's not bad. That's x equal 1. And if I look for the horizontal asymptote at, say, y equal, let's see, if I take the limit as x approaches infinity of 1 over x minus 1 minus 2x, as x approaches infinity, if I look at this, the denominator is growing with that bound that's going to approach 0. So what's the limit as x approaches infinity of that? That's negative infinity. Here we'll say it's none. Why is that? Because this is what you refer to as an oblique asymptote or a slant asymptote. A horizontal asymptote is a line that runs left to right. This graph has an asymptote that looks like this. And that's not what we want. This problem, again, vertical asymptote, that's simple. What's the domain? X cannot be 0. There it is. Horizontal asymptote, you would take the limit as x approaches infinity of 1 over x minus radical x. Well, obviously, anything over x approaches 0. So I'm left with the limit as x approaches infinity of negative radical x, and that's negative infinity again. We don't have any. Here we have an oblique or slant asymptote, depending on the author that you took. This is a bit tricky here. If you want to figure out the vertical asymptote, we have infinite amount of them. X equal, where does sine of x equal 0? Sine of x equals 0 at 0 and pi 2 pi. So when x equal 0 plus pi k, where k is all positive integers, there's an infinite amount of them. Horizontal asymptote, we say y equal, and let's see if I take the limit as x approaches infinity, assuming I stay away from those. This, if x is not multiple of pi k, then this will isolate between 1 and negative 1, the denominator. The top is approaching infinity, so pretty much it's going to oscillate between positive infinity and negative infinity. So this limit does not exist, and therefore we have none. The reason for that, this is going to grow bigger and bigger. The denominator, the sign, is going to keep on circling. In quadrant 1 it's positive, quadrant 2 it's positive, and then negative and negative, and that's where the positive and negative infinity come from. And if it keeps on oscillating, then the limit doesn't exist. Therefore, we have no horizontal asymptote. And there's the homework on this section.